In the previous two lectures, we were looking at correlations for momentum transfer. Okay. First for the flow in a pipe, an internal flow, and second for an external flow, flow past a flat plate. And in both of those cases, there was one salient feature of the flow that determined the form of the correlation. That was the laminar to turbulent transition. At relatively low Reynolds numbers, the flow is laminar. When the Reynolds number increases beyond a critical value, it becomes turbulent. And laminar and turbulent flows have very different characteristics. Laminar flows have straight, smooth streamlines, which are steady, and there are no fluctuations, and cross stream transport is due to molecular diffusion. In a turbulent flow, when the Reynolds number exceeds a critical value, transition takes place. There are large velocity fluctuations in the cross stream direction, and the transport of momentum and energy takes place due to eddies, which are parcels of fluid in correlated motion. And for a pipe flow, it takes place as the Reynolds number based upon the diameter and the average velocity exceeds about 2100. And we looked at correlations for laminar and turbulent flows. For a laminar flow, the friction factor is proportional to 1 over the Reynolds number. That is just a dimensional necessity. For a turbulent flow, the behavior is more complicated. The friction factor does depend upon the roughness of the wall of the pipe as well. Okay. And you have correlations like the Colebrook correlation for the friction factor, and as well as the Moody plots, which basically plot the log of the friction factor versus the log of the Reynolds number. And this is for a fully developed pipe flow, so that there is no variation in the velocity profile with downstream distance in the pipe. We looked at the case of a flat plate as well. Okay. In this case, the flow is not fully developed, though it may be steady on average. That is because the fluid that is incident on the plate, that is tangential to the plate surface, has to satisfy the no slip boundary condition at the surface of the plate. Therefore, the fluid is retarded by the stress or the force exerted by the fluid on the surface, and the effect of the plate, okay, the distance to which the flow is retarded due to the presence of the plate, increases with downstream distance as momentum diffuses further and further away from the plate. That distance, which I defined as delta 0.99, okay, the distance at which the velocity reaches 99% of its free stream velocity, it increases as r e power minus half, or it increases as the square root of the downstream distance, okay, for a laminar flow. Okay. When the Reynolds number based upon the distance from the upstream edge, okay, in this case the Reynolds number is based upon the distance from the upstream edge of the plate, x, not the total length of the plate. When the Reynolds number based upon the distance from the upstream edge exceeds a critical value, in this case 5 times 10 power 5, there is a transition to a turbulent flow. And in a turbulent flow, the boundary layer thickness goes as r e power minus 1/5 rather than r e power minus half. Okay. And the drag coefficients we had discussed, okay, the drag, the skin friction coefficient, which is based upon the average stress on the plate, the force per unit area that is tangential to the flow, that is proportional to r e power minus 1/2 for a laminar flow and r e power minus 1/5 for a turbulent flow. Okay. So, in each of these cases, we had a clear distinction between two very characteristic types of velocity profiles, the laminar and the turbulent flow. Next, we will consider the flow past a spherical particle. Okay. of diameter d, okay, and the Reynolds number for that particle is defined as rho v free stream times d by mu, okay, where d is the diameter of the spherical particle. If it were not spherical, you would use the equivalent diameter and the free stream velocity. So, this is for example, a particle settling in a fluid. Okay. If it is settling at its terminal velocity, then the v free stream is basically the terminal velocity of the particle, because it is the difference between the particle velocity and the fluid velocity far from the particle. If you had, for example, air blown at a spherical object, that would be the velocity with which air is blown past that object. That would be the free stream velocity. The velocity far from the object in the fluid minus the velocity of the object itself, which in this latter example is 0. So, this is the Reynolds number. In the case of pipe flow and flow past a flat plate, there was one distinct transition. Okay. In the flow past a sphere, there are many characteristics that flow characteristics that change as the Reynolds number is increased, and I will describe for you each of those in some detail, okay, in order to demonstrate the kinds of complications that arise when you have flow past a spherical particle. Okay. So, if the Reynolds number is small, okay, Reynolds number small is approximately Reynolds number less than about 1.5 or so. Okay. Rho v free stream into d by mu is less than about 1.5 or so. Okay. And if you have fluid that is incident on the spherical particle, and if you look at the streamlines, these streamlines have symmetry between the upper and the lower hemisphere, of course, okay, because this is an axisymmetric problem. You have a sphere in a free stream velocity, and therefore, at a given distance from the axis, okay, and at a given downstream distance, if you change the angle around the axis, there is no change in the velocity. Okay. When the Reynolds number is low, there is also symmetry between the upstream and the downstream hemispheres. Okay. The velocity profile in the downstream hemisphere and the upstream hemisphere, okay, are symmetric, okay, about this mid plane, okay, perpendicular to the direction of the flow. Okay. This is what is classically called as a laminar flow for the flow past a spherical particle, and the Reynolds number is less than about 1.5. Okay. So, whatever if you take the velocity on some upstream location, okay, the velocity is in this direction, at a downstream location which makes the same angle, okay, at a downstream location which makes the same angle, the velocity will be the same in the flow direction and reversed in the direction perpendicular to the flow. Okay. So, if the velocity is in this direction in the upstream location, the velocity component along the flow direction is the same at a downstream distance, downstream location which has the same angle, okay, about the hemisphere, and the velocity perpendicular to the flow direction will be exactly reversed. Okay. When the Reynolds number increases to about in the range 1.5 to about 24. Okay. There is no longer symmetry between the upstream and the downstream hemispheres. Okay. What you get is a velocity profile that is now not symmetric. Okay. In other words, the distance of the streamline from the axis far from the sphere on the upstream and the downstream sides are no longer the same. Okay. So, there is an asymmetry between the upstream and the downstream locations, and when you increase the Reynolds number further in the range of about in the range about 24 to about 400 or so. Okay. The flow what is called detaches from the surface, okay, on the downstream side. Okay. So, you have something called a separation bubble on the downstream side, within which the fluid is always recirculating. Okay. So, recall that for this case, okay, the fluid comes in, okay, at on the upstream side at minus infinity and leaves at plus infinity. Okay. That is valid for all of the fluid, okay, that is flowing past. In this particular case, the fluid within the separation bubble, okay, is recirculating, and the fluid outside that, okay, has asymmetric trajectories. Okay. This recirculation is steady within that separation bubble. So, as far as the flow is concerned, right, the region within this separation bubble is not accessible to the fluid that is flowing past the surface. Okay. So, the object has a sort of a modified shape, okay, with a separation bubble at the rear. Okay. That happens when the Reynolds number is in the range of about 24 to about 400 or so. When the Reynolds number exceeds about 400, okay, you get what is called a wake formation at the rear. Okay. So, okay, on this rear side you have wakes that are, okay, unsteady. Okay. Okay. You have what is called, okay, so this is what is called a separation bubble. At the rear. In this case, you have what is called vortex shedding. Okay. Vortices, which are basically circulating parcels of fluid, right, emerge from this particle at the back in what is called the wake, and they are convected and they are they detach from the particle and they travel downstream. Okay. This happens when the Reynolds number is in the range about 400 less than Reynolds number less than 4000 or so. Okay. All of these limits are not exact, okay, they are approximate limits, okay, in all cases. Okay. So, you have this periodic vortex shedding, the flow is no longer steady on the downstream side. Okay. You have periodic vortex shedding, whereas the upstream side there is a steady flow. Okay. And this periodic vortex shedding happens in a region that is called the wake. Okay. The wake behind the particle, okay, within which there is periodic vortex shedding. Okay. Further increase the Reynolds number. Okay. The Reynolds number in the range about 4000 2 into 10 power 5. Okay. In this case, you have a region at the downstream side where, okay, there is turbulence. Okay. So, let me just draw it more exactly. Okay. You have this region in this downstream side, okay, where you have turbulence in the wake. Okay. The fluid that is incident, okay, goes around this region, okay, and that fluid that is going around does not have turbulence, but within this wake region there is turbulence. Okay. And this wake region starts at a location that is slightly upstream of the mid plane of the sphere. Okay. This wake region starts at a location that is slightly upstream of the mid plane of the sphere, and the flow outside of this wake region, okay, in the upstream region is all laminar, okay, and there is turbulence in the wake. Okay. And as you increase the Reynolds number further, okay, as you increase the Reynolds number further, okay, and the Reynolds number is greater than about 2 into 10 power 5. Okay. Two things happen. One is that this wake region suddenly moves downstream. Okay. This wake region suddenly moves downstream almost discontinuously. Okay. and there is turbulence on the upstream side also, where the fluid is incident on the particle, okay, what is called the boundary layer region, similar to what we had for a flat plate. Okay. The boundary layer on the upstream side also becomes turbulent, similar to what we had in the case of a flat plate. The wake region shifts suddenly to the downstream location, and there is turbulence in the downstream wake as well. Okay. So, a rather complicated set of transitions that take place in this particular case, some of which are gradual and some of which are abrupt. Okay. Yeah. So, this is a simplistic summary of the various things that happen in the flow past a spherical particle. How does that affect the drag force, okay, for the flow past a spherical particle? Okay. Recall that we had defined the drag coefficient, okay, as the drag force divided by the projected area divided by the kinetic energy density. Okay. So, for a spherical particle, okay, with flow that is incident on it, the projected area is the area of the circle, okay, the circle which is perpendicular to the flow, okay, that is the projected area. Okay. The total drag force divided by the projected area divided by half rho v square is the drag coefficient. So, this is like a pressure difference due to a pressure difference between the upstream and the downstream side. Okay. The pressure difference will be the total force, the average pressure difference will be the total force exerted divided by the projected area, because the force exerted by the pressure on the upstream side is along the flow direction, whereas the pressure on the downstream side is perpendicular to the flow direction. So, if I take the average pressure difference and multiply it by the projected area, I get the total force, and that is divided by the average kinetic energy in the free stream. Okay. At low Reynolds number, okay, the drag force cannot depend upon the density, okay, because low Reynolds number implies that inertial effects are much smaller than viscous effects. Okay. Recall that the Reynolds number is equal to rho VFS d by mu. So, when the Reynolds number is small, inertial effects are much smaller than viscous effects. Okay. And just from dimensional analysis, if you recall the very first problem that we solved, we know that Fd is equal to a constant into mu Vfs times d from dimensional analysis at low Reynolds number. Okay. That means that the drag coefficient is equal to Fd by pi d squared by 4. Okay. The projected area is pi d square by 4, where d is the diameter, divided by half rho v free stream square. Okay. And since I have a density in the denominator here in the kinetic energy per unit volume, and the drag force has to be proportional to the viscosity, right, it is quite easy to see that this will be proportional to 1 over the Reynolds number. For the particular case of a sphere, if you recall, we said that this constant was 3 pi, okay, and if you put this constant in here, okay, the exact value for a spherical particle is 24 by Re, okay, CD for a spherical particle in a laminar flow viscous limit where inertial forces are not important. Okay. On the other hand, if you are in a completely inertial regime, okay, if a completely inertial regime where there is no symmetry between the upstream and the downstream sides, okay, typically the force, the pressure exerted in this wake region is much smaller than the pressure exerted on the upstream side. Okay. The reason is because on the upstream side the fluid velocity is incident on the sphere, okay. Therefore, it exerts a force on the sphere, whereas once there is a wake developed at the downstream side, you do not have a similar velocity incident on the sphere on the downstream side. due to which the pressure exerted on the hemisphere on the downstream side is much smaller than that exerted on the upstream side. And therefore, in the limit of high Reynolds number, the drag force will not depend upon the viscosity, okay, because it is due to a pressure difference between the upstream and the downstream sides, in contrast to a flat plate where it is due to the viscous stress exerted at the surface. In that case, it does depend upon viscosity. In this case, because it is due to a pressure difference, it does not depend upon viscosity, which means that the drag coefficient has to tend to a constant value. Okay. This is for low RE, and CD is equal to a constant for high RE. Okay. This is what you would expect. Okay. And to some extent, that is what is actually followed that is what is actually observed in the flow past a spherical particle. Okay. So, if I plot once again, okay, log of the drag coefficient versus log of the Reynolds number, okay, in a log-log plot, okay, and I can have various limits here. This is about 1.5, say, Reynolds number. Okay, I have about 24. Then I have 400 and about 4000 and 2 into 10 power 5. Okay. So, I am plotting the x axis on a log graph and the y axis also on a log graph. Okay. And these different ranges are the ranges corresponding to the different kinds of flow characteristics that are observed in this figure here. Okay. The ranges for the different kinds of flow characteristics in this figure here. Okay. So, those are the ranges I am plotting. Less than about 1.5, CD is 24 by RE, therefore, log CD will be equal to, I should note here that what is usually plotted is the logarithmic, but I will refer to it as ln, okay, just to avoid any confusion. I will use the natural log everywhere. Okay. Okay. Is equal to ln 24 minus ln RE. Okay. Therefore, we have a line of slope 1. Okay. As you exceed about 1.5, there is no longer a straight line. Okay. So, let me put some numbers here. This CD is 1 and this is CD about 0.5. Okay. You depart from linearity as you exceed this. Okay. And at about, let me see, at about a Reynolds number of about 4000. So, I should. So, the power is minus 1 here. Okay. And then it departs from linearity. So, if I extended the laminar profile, it will look something like this, but the curve actually decreases, and at about a Reynolds number of between 400 and 4000, okay, it saturates at a value of approximately 0.5, okay, and it continues that for a while. And then when you exceed this value of 2 to 10 power 5, there is a sudden decrease. Okay. Okay. It is called the drag crisis. Okay. There is a sudden decrease in the drag coefficient versus Reynolds number. Okay. This transition, this sudden abrupt decrease, okay, is because of what I had shown here, that when you go at about 2.5 to 10 power 5, there is a transition from a flow with the wake starting slightly upstream of the hemisphere that is facing the flow, to something that goes further downstream, okay, and turbulence in the wake. Okay. That corresponds to this transition, corresponds to this transition over here. Okay. It is linear for about up to about 1.5, and then it starts to depart from that linearity, and it approaches about 1/2, okay, about 0.5, okay, it approaches a value of about 0.5, okay, in the range between about 4000 and 2 into 10 power 5. So, in this region it is approximately a constant, okay, as we would expect from dimensional analysis. Okay. In this region it is approximately a constant as we would expect from dimensional analysis. If viscosity was not a parameter, then the drag coefficient has to be a constant. That constant value is about 0.5. Here it is about 1 over Re, okay, as we would expect from dimensional analysis if drag was entirely viscous and density had no effect on the drag force. Okay. And in between there is a smooth transition. Okay. So, the viscous laminar flow correlation CD is equal to 24 by Re is valid for Re less than approximately 1.5. Okay. There is a correction to this drag correlation. It is called the Schiller correlation. CD is equal to 24 by Re into 1 plus 0.15 Re per 0.687. This is an empirical correlation. Okay, this is an empirical correlation, and this works for Re less than approximately 400 or so. Okay. Okay, this gives you an accurate result. It captures this entire region. Okay, so it captures this entire region. Okay, up to a drag coefficient of about 400 or so. Okay, beyond which it starts to underpredict the drag coefficient. Okay, and then there is this constant value here in the range between about 4000 and 2 into 10 power 5, where the drag coefficient is approximately 0.5 or so. Okay. And then there is this drag crisis where the drag discontinuously decreases. Okay. So, I should make a correction here, this is not 0.5, this is about 0.4. Okay. Please note that this constant value that is observed here is about approximately 0.4. Okay. And then after that there is this abrupt drag crisis, okay, and it goes to a lower value of the drag coefficient on this log plot. Okay. So, the force on the sphere depends upon which regime we are in. Okay. You have multiple regimes depending upon the nature of the flow around the sphere. Okay. A similar thing applies to a cylinder as well, except that the Reynolds number for different kinds of transitions are different in the case of a cylinder, but the same broad picture applies in that case as well. Okay. And depending upon what regime you are in, you can calculate what is the drag coefficient, and from that we can find out what is the force exerted on the sphere. Okay. So, this is a summary of the drag coefficient for the flow past a sphere and the types of velocities, the types of flow profiles, the types of characteristic flow patterns that are seen in the flow past a sphere. Okay. So, this is sort of different from a flat plate or a pipe where you see a transition between only two distinct regimes. Okay. Here you see multiple regimes, okay, as the Reynolds number of the flow past the particle is increased. Okay. So, next lecture I will solve a problem to show you for a particle of a particular diameter settling in air, what is the velocity and what is the particle diameter for which all of these characteristic behaviors are observed. Okay. That will give us a physical picture of the kinds of flow profiles that we will see if we were to drop in air particles of different sizes. Okay. So, that I will continue in the next lecture, okay, and before we go on to looking at what is the drag coefficient for flow past a bubble. The difference between a bubble and a particle I will discuss at some length. For a particle at the surface, the fluid velocity is equal to the particle velocity, which means that at the surface of the particle, if it is stationary, the fluid velocity has to decrease to 0. A bubble does not have a rigid surface, and because of that the velocity does not have to decrease to 0. You can have a finite velocity in the fluid at the surface of the bubble, and because of that the correlations for a bubble are different from the correlations for a particle or for a drop for that matter. So, that we will discuss in the next lecture. We will see you then.